All right. Now suppose you need to run some regressions that are a little bit more involved than simply regressing some continuous x variable on some continuous y variable. Not a problem. So we're going to walk through the 4 different ways that this might happen. So the first thing that you might want to do is take the log of a variable. So suppose I'm using, if I scroll up here, I've already kind of like cleaned my data. Everything's ready to go. My variables are ready to use. Created dummies where necessary, etc. Drop the samples that I didn't want. Ready to go. Okay. So I have this data frame called salary, and maybe I want to run a regression for salary as explained by a dummy for do you have an econ degree, but maybe I want to take the log of salary. That's fine. All we need to do is put log salary inside of the linear model function and run it. And first error that I have, and this is I guess a warning, I don't have a variable called salary, it's called inc wage. I should really just go and change that in here with a rename because I seem to like typing salary, but we'll leave it for now. So I guess the warning is name your variables the things that you will remember. There we go. So it says, at least among the people in my data, people with econ degrees have 24% higher salaries than people without. And because it's a random sample of the population, we can then go up from there and say having an econ degree as opposed to another degree increases your salary, or at least is associated with a 24% increase in your salary. Right? We can take a log of the x variable here too. If we want to log x, that's totally fine. Here we go. But of course, you can't take the log of a variable that has a 0 in it. So you can't take the log of a dummy. You wouldn't want to anyways. But you might want to take the log of a continuous variable like age. So when we run that, we find that a 1% increase in age increases or is associated with an increase in salary of 0.43%. Or what we have here is an elasticity of salary with respect to age. It's inelastic, which suggests basically that your age tends to increase faster than your salary does, at least in percent form. So your salary tends to increase as you age, but not as fast as your age does. That's what it says. And that's logs. All we need to do is put log right into the lm function. All right, next, you might want to put a squared term. You might think that there's a variable that affects y, but it's not in a straight line. Totally fine. There's a couple ways to do this. So suppose we want to I want to know how wage is affected by age, but not just in a straight line. I want to allow it to make a curved line. It'll choose the parameters to make the curve minimize the squared errors. That's fine. There's a couple ways to do that. First, you can run a little mutate here. You could say, create this variable called age squared, where it's just age times age. And pipe to your linear model and put plus age squared there. That's totally fine. We run it. Okay, and we get this negative term on age squared, which suggests it's an upside down U shape. Cool. Now, I like efficient coding, so there's a second way to do this, which is this I function. I says I want to mess with the variables here inside of this function. So all we need to do here is put age to the power 2. Okay, we run that. We get the same results, and with one less line of code. We only added, just a few letters there. Totally fine as well. And that's it. That's squared terms. There we did it. Cool. Interpreting this is, of course, a little bit difficult. You will refer back to our notes, our slides. It's essentially the derivative of this estimated line with respect to age. So you get this as a constant. Every time you age by a year, your salary goes up, or at least in correlations, it goes up by this much. And take this 1 times 2 and multiply it by age. There's your function for how a 1 year increase in age is affected or affects your salary. Of course, it depends on where the age is because it's non-linear. Okay. We did it. Next, dummies. So I have this variable called, this data frame called employed, where I want to know how some of these labor market factors might affect the probability of being employed. So my dummy here is just employed. You have a job. It says 0 or 1. and I might put econ degree. And that's it. If you want to run a regression with a dummy as a y variable, just put it in there. R is going to minimize the squared errors with these coefficients, and you're good to go. So this says that having an econ degree as opposed to the other degrees represented in the data tends to, or is associated with, an increase in the probability being employed by 6.3 percentage points. Non-econ degree holders, 68.6% of them are employed. That's what that shows. And we did it, dummy wise. There we go. Last one, interactions. Suppose we want to know not only how having an econ degree affects employment probability. Maybe we want to know, same results. We want to know how different is this for men and women. So I can add a female dummy here. We will always do this if we're going to run. If you have an interaction in your model, you need to have both of the interacted variables represented already in the regression equation. So then I can do an interaction here with econ and female, but there's two different ways of doing this as well. So one, the less efficient way is I can say, well, let's just create a variable called interaction, and interaction is econ times female, just like we did with the square term. That's fine. Put interaction here. Run it. So what this shows is that having an econ degree for men, having an econ degree increases or is associated with an increase in employment probability of 2.57 or 2.6 percentage points. And this interaction term says that this relationship between having an econ degree and employment is 8 percentage points stronger for women. Or you could add these together and say that having for women, having an econ degree instead of an alternative degree as represented in the data increases employment probability by this one plus this one. 10.7 percentage points. Pretty cool. Now, if we want to get efficient with your coding, we don't necessarily need this. We can just use this I function again and say, look, interact econ times female. Put that there. Run it. Same results, more efficient coding, and that will allow you to estimate models with an interaction term.